Hello, everybody. So the results I'm going to present today are part of what I did during my master's. And when I started my master's in 2018, my advisor said, we have this bunch of forestry data and we have to do something with them. And I was a little bit disappointed because I wanted to get down to the cool hydrologic modeling stuff, such as surface modeling and groundwater modeling, things like that. And I wasn't much into forestry and forest modeling in general. But I quickly learned how important forests are in the hydrologic cycle, how they can interact with precipitation, intercept incoming water from precipitation through their canopy, and this water becomes immediately available for evapotranspiration, and as a consequence, it reduces the surface runoff rates, for example, and consequently the amount of water reaching water bodies. And in the southeastern United States, we have two major tree species. We have the loblolly pine species, which is the dominant pine species in the southeastern United States and also in the United States as a whole, and also the slash pine, the second most dominant species in this region. And we know that models have been used more and more in the field of hydrologic sciences, as in basically any other field. And we want our models to be good predictors of the natural system, and we want our models to be as reliable as possible. But although these models have been more and more used throughout the last few decades, the modelers, the users, they usually do not care much about forest processes in the watershed. They're like me when I started my master's. Like, we want to get to the surface water or the groundwater, but we don't pay much attention to what's happening within the watershed. And as a consequence, vegetation in general, it doesn't get much attention in hydrologic modeling. And it can become a problem because we know how important forests are in the hydrologic cycle. And if models are being more and more used and we want our models to be reliable predictors, we should include these important processes such as evapotranspiration, canopy interception, water uptake to the plant roots and such. So it leads us to two research questions for this little project. Like, we want to know if forest dynamics are realistically represented in watershed models, and if not, can they be improved? And to answer these research questions, our approach was model calibration against some key forest processes such as leaf area index, biomass, and evapotranspiration. And our second research question is, what is the impact of forest growing dynamics on the hydrological predictions of watershed models? And for that, we designed some modeling experiments in which we progressively constrain our model with observations of different forest processes. And we are going to discuss more about this in a second. So in general, how this is a very simplified slide explaining basically how we parameterize the SWAT model so that it could handle slash pine and loblolly pine. Basically, we inserted these three species in the model's plant database, and then we parameterize the model. We improve the default parameter values representing these forest processes. And we did that through data fitting techniques, lit review, data from field observations, also remote sensing data and expert knowledge. And then we calibrated these key processes such as LAI, biomass, and evapotranspiration against observations and assessed the model performance against some statistical rating metrics. And when we reach satisfactory rating criteria, we consider our model calibrated or a satisfactory predictor of forest processes. Sorry. So after we conducted this, we implemented these forest processes into the model. We tested its robustness in two watersheds in the southeastern United States. One watershed is located in Georgia. It's the Apatoy Creek watershed, and it is basically dominated by loblolly pine. And another watershed is located in Florida, and it is basically dominated by slash pine. And other than that, these two watersheds, they are similar in terms of area, annual precipitation, annual temperature, and also discharge and potential evapotranspiration. Now, the main difference is the land use land cover of these watersheds. As I said, the watershed in Georgia, it's dominated by loblolly pine. And the watershed located in Florida, it's dominated by slash pine. So because the land use land cover maps such as the NLCD, they do not have a high level of discretization of land use, land cover classes, we performed the reclassification so that what NLCD classifies as evergreen forest could be actually discretized into different forest species, for example. For that, we use the USDA's National Forest Type dataset. When, after running some GIS routines, we are able to, for example, for the evergreen species in Georgia, we realized that what NLCD classifies as 30% evergreen is actually 4% after the reclassification, and it becomes 57% of loblolly pine. And similar for the watershed in Florida. Like previously, based on NLCD, we had 40% of evergreen. Now, after reclassification, we went down to 5%, and 56% of the watershed is actually covered by slash pine species. So that is good because we know exactly where in the watershed we have slash pine and where in watershed have loblolly pine. So we can transfer the model parameters, develop at a field scale based on field observations and other techniques to these models, to these locations, and then we could assess the model performance at specific locations across the watershed area. So as I mentioned before, I had 4 experimental experiments, so calling this experimental design. So our first experiment, we basically, I call it the default model. We set up and run the SWAT model. We set up the best model we could, but we did not touch upon forest processes. For our second experiments, I'm calling it model ET. For these experiments, we included to the model parameters previously calibrated against evapotranspiration. So this experiment includes evapotranspiration dynamics into the model. In the third experiment, we remove evapotranspiration, but we included LAI and biomass. And the fourth experiment is basically the most sophisticated model that we could build. We consider in this model, we consider leaf area index, biomass, and also evapotranspiration. So comparison of each one of these models, 2, 3, and 4, against the default model tells us how much the addition of evapotranspiration contributes to the model performance, or how much the contribution of LAI and biomass added to the model, and what is the contribution of the 3 of them together. Also, we performed 2 calibration techniques for this project. The first approach used was a traditional calibration approach, where we assess the model performance in predicting Streamflow at the watershed outlet. And our second calibration approach, we call it a multifaceted calibration approach, because we not only calibrate Streamflow, but we also take care of processes happening between the watershed outlet and upland areas. And when I say processes happening between the watershed outlet and upland areas, for this case specifically, I'm talking about forest processes, leaf area index, evapotranspiration, and biomass. So getting down to the results, this is the hydrological responses of the model before calibration. So we can see in this left panel right here, the Apatoy Creek watershed, and we have 4 experiments, the ones we described earlier one. So in terms of metrics, we can see that our default model, it was overestimating Streamflow by 66%. And after we included evapotranspiration into the model performance, it improved a lot. It went for a NASH of 0.19 to 0.64, and the model overestimation dropped from 66% to 12%. And that's for Georgia, the watershed dominated by loblolly pine. And after we remove ET from the model, but added leaf area index and biomass, the model performance dropped in relation to its default. And also the overestimation increased. But after we added back evapotranspiration and also considered leaf area index and the biomass, this is our most sophisticated model. We can see that the model performance, again, improved considerably, and also the overestimation dropped. And the same thing for the Santa Fe River watershed, the one dominated by loblolly pine trees. We can see that the default model had a NASH of minus 0.36. After adding evapotranspiration, improved to 0.15. When we remove ET but added LAI and biomass, the model performance dropped a little bit, but it was still an improvement in relation to its default settings. And when we added evapotranspiration plus LAI plus biomass, we reached the best model performance. Let me go back to the right panel shows the monthly hydrograph. It's in terms of performance, the performance a little bit higher, but the trends are the same. After we added evapotranspiration to the model, we reached the best performance for loblolly pine in Georgia. And for the slash pine watershed in Florida, we reached the best model performance after we added LAI, biomass, and evapotranspiration to the model. And in general, we basically we decreased the model overestimation with Streamflow that was being predicted under the default settings when we consider the forest dynamics into the model. And in terms of baseflow, we can see a similar scenario. The default model was overestimating baseflow by 55% in Georgia. And after we added evapotranspiration, leaf area index, and biomass to the model, not only the model performance in terms of goodness of fit improved, but also the overestimation declined to a little bit over 1%. And in Florida, same thing. We had a terrible predictor model under its default setting with a national -8. After we added LAI, biomass, and ET, we were able to, went up to -1. It's still not a good model, but it's a model, its performance improved a lot after we consider forest dynamics into the model, and also the overestimation reduced a lot. And the right panel shows the water budget of the watershed after we consider each one of these experiments into the model. We can see there's a huge difference between the default model and the most sophisticated model. And this difference, it's mainly in the direction of higher evapotranspiration and lower surface runoff, base flow, and lateral flow after we consider the forest dynamics into the model. And remember, all of these experiments, they are conducted before calibration, right? We wanted to see what's the impact of ET, LAI, and biomass in the model performance in relation to Streamflow. And the takeaway message is that evapotranspiration seems to add the most to the model. And after the next step, we conducted model calibration at the watershed outlets using two different approaches. So comparing these two approaches, we can see the monthly hydrographs here, and we can see the daily flow duration curves. And in terms of performance, we can see that we had a good calibrated model using the default calibration, the traditional calibration, taking care only of the stream flow at the outlet and not touching upon the forest dynamics. But when we calibrated first the forest dynamics, and then we performed stream flow calibration at the outlet, we were able to improve the model performance. And that was not only to the watershed in Georgia, but also to the watershed in Florida. So as conclusions for this study, we can say that the improved representation of forest process in SWAT returned better stream flow and base flow predictions. And also our results suggest that evapotranspiration is the main reason leading to a more accurate stream flow and base flow prediction in watershed models, because it showed more improvements in the model performance compared to leaf area index and biomass. And also the improvements in forest process substantially alter the watershed water budgets toward increased evapotranspiration and decreased surface and subsurface water fluxes. So the takeaway message here is, by default, SWAT was largely underestimating evapotranspiration at both watersheds, and this underestimation of evapotranspiration was leading to an overestimation of stream flow. And finally, our findings suggest that key forest processes such as LAI, biomass, and ET, they should actually be improved in hydrological models before simulating stream flow, as our calibration, our multifaceted calibration approach demonstrates. Once we take care of these forest processes before conducting any stream flow calibration at the watershed outlet, we can reach better stream flow performance, a better model performance in predicting stream flow, meaning that we can not only have a good model predicting stream flow, but we can also have a good model predicting intra-watershed processes such as vegetation components. So with that, I leave the floor. If you have any questions, please feel free to reach out to me through this email, and thank you for your time.